Until now, we've been studying models that directly distinguish one class from another. These are called discriminative models. Today, we'll see a different type of classifiers called generative models that model the entire generation process, which can also be used to classify instances. First, we'll study the basics of Bayesian networks. A Bayesian network is a DAG capturing the conditional independence of the random variables. Every node in a Bayesian network is a random variable, and every directed edge represents a conditional dependence. So if there's a directed edge from node X to node Y, that means the random variable X has a direct influence on Y. And here, direct influence is often causal. And each node has a conditional probability of P of that random variable given all the parents. So this is just P of W, P of CY, P of T given CY, and P of CH given CY. And here's an example of n independent coin flips. Because these coin flips are independent, we have n nodes without any edges. And each node comes with a probability table, 0.5 for head and 0.5 for tail. Note that we have n tables with 2 rows each, so we have 2 times n rows. But if we were to use a full joint table to represent the probabilities, we would have needed a table with 2 to the n rows, 1 row for every possible combination of heads and tails. Bayesian networks can actually help you save memory if you have a lot of independent random variables. Here's another simple example where we have 2 random variables, S and T, and S represents whether it's snowy and T represents whether there's a traffic. Since S doesn't have any parent, we'll have a table for the probability of S, and since T has a parent S, we'll need a table for the probability of T given S. Notice that we have enough information to infer the probability of T, which would just be the probability of having traffic, regardless of snow, over all possibilities. From here, it's simple math. And this is called inference by enumeration. Let's look at a bit more complicated example. Suppose I'm at work and my neighbor, John, calls and tells me that my alarm is ringing, but my other neighbor, Mary, didn't call me. And the alarm can be set off by minor earthquakes or a burglar. What would be the Bayesian network for this problem? We have 5 variables, and the first dependence we have is burglar can set off the alarm. And we also have the earthquake setting off the alarm. And then once we have alarm, then John could call or Mary could call. The resulting Bayesian network looks like this. And as you already know, every node comes with a probability table. It's the probability of the given random variable given all the parents. B and E don't have any parents, so we just have probability of B and probability of E. A has 2 parents, B and E, so we need probability of A given B and E. And then similarly, we need probability of J given A and probability of M given A. So these are all our tables that go with the Bayesian network. And we already talked about this when we were discussing the n coin flips example, but Bayesian networks can save you a lot of memory if there are a lot of independent variables. More generally, if you have n random variables, each with at most k parents, then you only need big O of n times 2 to k rows. Whereas if you were to build a full joint probability table, we'll need big O of 2 to the n rows. And because independence between random variables helps us simplify the tables as well as inference, we often ask the question, are 2 nodes independent given some network structure? And there are 3 canonical structures: causal chain, common cause, and common effect. Let's first review what it means for two random variables to be independent. X and z are independent if p of x and z is the same as p of x times p of z. And we can compare this to p of x and z, and using chain rule, p of x times p of z given x. So in other words, x and z are independent if p of z is the same as p of z given x. And x and z are conditionally independent given y if p of x and z given y is the same as p of x given y times p of z given y. Again, we can compare this to p of x and z given y and using chain rule. So we have p of x given y times p of z given x and y. So in other words, x and z are conditionally independent if p of z given y is the same as p of z given x and y. Now, the first structure, causal chain, is where we have three random variables forming a chain. So for example, let's say x is went to a party, y is procrastinate, and z is students panicking. This Bayesian network says students panicking is dependent on students procrastinating, which in turn depends on students going to a party. The first question we can ask is, are x and z independent? The answer is no, because students panicking is dependent on procrastinating, which in turn depends on going to a party. Then are x and z independent given y? The answer is yes. Once you know whether the student procrastinated or not, going to a party and panicking are independent. And this can easily be shown through some simple probability. We want to show that the probability of x and z given y is the same as the probability of x given y times the probability of z given y. Well, the probability of xz given y is the same as probability of x given y times probability of z given x and y using chain rule. And then consider the probability of x, y, and z. If you look at the Bayesian network, the probability of x, y, and z all happening is just the probability of x times probability of y given x times probability of z given y. But we also know, using chain rule, that this is the same as probability of x times probability of y given x, probability of z given x and y. So we know that the probability of z given y and probability of z given x and y are the same. So we have probability of x given y times probability of z given y. Therefore, x and z are independent given y. The second structure is common cause, where we have two random variables dependent on a single random variable. For example, we could have the class being full and students being sleepy, both dependent on whether the homework was due the night before. And we can ask the same questions. First, are x and z independent? And the answer is no. Because, for example, if we know that the class was full or not, then we have some sense of whether the homework was due the night before or not. And that information, in turn, can be used to determine whether the students are being sleepy or not. Now, are x and z independent given y? The answer is yes. So once you know whether the homework was due the night before or not, knowing whether the class is full or not doesn't help us determine if the students are sleepy. We can again show this mathematically. The probability of x and z given y is the probability of x given y times probability of z given x and y. Again, the probability of x, y, and z all happening is the same as the probability of x given y times the probability of z given y times the probability of y. And that's based on the structure. But using the chain rule, we also know that this equals the probability of y times probability of x given y times probability of z given x and y. So from here, we know that the probability of z given y is the same as the probability of z given x and y. So again, this thing becomes probability of x given y, the probability of z given y. The last structure we're going to look at is common effect, where one random variable is dependent on two random variables. For example, having a traffic depends on both whether it's raining and whether there's a ball game. Now, are x and z independent? The answer is yes, because whether it's raining or not has nothing to do with whether there's a ball game or not. And we can show this mathematically. The probability of x, y, and z all happening is the probability of x times probability of z times probability of y given x and z. And that's based on this structure. And we also know, using the chain rule, we have probability of x times probability of z given x times probability of y given x and z. So we know that the probability of z is the same as the probability of z given x. So the probability of x and z is the same as the probability of x times probability of z given x by chain rule. So this is just probability of x times the probability of z. Okay, so this whole thing is for the first question. And the second question is, are x and z independent given y? Given that you know whether there's a traffic or not, are raining and having a ball game independent? The answer is no. Suppose both raining and ball game each contribute to there being a traffic. And suppose you know that there's a traffic. Then, if we happen to know that it's not raining, then it's more likely that there's a ball game, and vice versa. And now we'll study how Bayesian networks can be used to build a classifier. We'll study one type of such classifiers called naive Bayes classifier, which is the most popular of all Bayesian network classifiers. As we've seen, Bayesian networks can capture a very complicated conditional dependence structure. In naive Bayes classifier, however, we actually have a very simple structure where we have n random variables dependent on a single random variable. And this is actually a structure we've seen before called common cause. And in the common cause structure, given the cause, the effects are all independent. In other words, f1 through fn are independent given the class. And this independence assumption is where the name naive comes from. So we're naively assuming that the features are independent given the class. And here, an example of class would be positive, neutral, and negative for sentiment analysis. And features could be the words. For example, f1 could be, is the word happy in the text? And f2 could be, is the word sad in the text? And so on. And suppose the probability table looks like this. For any given piece of text, the probability of it having positive sentiment is 20%, neutral is 47%, and negative is 33%. The probability of each fi given C is as follows. Okay, perhaps this is a good table for F1. So given that the sentiment is positive, there's a 95% chance of it containing the word happy. And if the text has negative sentiment, then it has 94% chance of it not containing the word happy. Okay, realistically, 95 and 94 are too big. So this is a very exaggerated example, but nonetheless, you get the point here. The question is, how do you use this Bayesian network to build a classifier? As an example, let's consider the email classification again. So we're trying to decide whether a given email is spam or not spam. And here, unseen just means unseen during training. Well, we compute the probability of the class given the email for every class and pick whichever class has the highest probability. So for example, if the probability of spam given the given email is greater than the probability of it not being a spam given the same email, then we classify it as spam and not spam otherwise. Now the question is, how do you compute these probabilities? A very naive approach would be we just count the number of times the given email appears as spam over the number of times the given email appears in the training corpus. And as you would expect, this is not a good approach. Because it's very unlikely that the email we're trying to classify appears in the training set at all. So it's just 0 over 0. So we need a better approach. As an aside, let's look at the Bayes rule. The probability of A and B can be factored in two different ways. Probability of A given B times probability of B, or probability of B given A times probability of A. And if you just divide both sides by the probability of B, you get the Bayes rule. So we have the probability of A given B is the same as probability of B given A times probability of A over probability of B. One interpretation of Bayes' rule is this. This is called prior probability. So before seeing anything, you believe that A is true with certain probability. And this is called the posterior probability. So given that you have seen B, now you believe A is true with what probability? And this is called likelihood. How likely is to observe B given A? And lastly, this is called evidence. So regardless of A, how likely is it to see B? So for example, suppose A is the person behind me is female, and B is we are in line for women's bathroom. So P of A would be the probability that the person behind is female, which is, say, I don't know, 40%. Whereas P of A given B would be the probability that the person behind is female given that we're in line for women's bathroom, which is probably higher. And P of B given A is given that the person behind is female, what's the probability that we're in line for women's bathroom? And P of B is, regardless of the gender of the person behind, what's the probability of we being in line for women's bathroom. Now, going back to the Naive classifier, we're trying to find the class C that maximizes the probability of C given E. And as we have discussed, directly estimating this probability is not easy. So what we're going to do is we're going to use Bayes' rule. So this is the same as argmax over C, the probability of E given C times probability of C over probability of E. And notice that we're comparing different C's, and P of E doesn't change, so we can ignore that. Argmax C, P of E given C times P of C. Then we represent E using a bunch of features, say F1 through Fn. We now have argmax P of F1 Fn given C, P C, which is the same as argmax C P F1 given C times P F2 given F1 and C times P of F3 given F1 and F2 and C and so on, and PC. And that's using the chain rule. In Naive, we know that we have this common cause structure. So given C, all the features are independent. In other words, we have argmax P of F1 given C, P of F2 given C, P of F3 given C, and so on and so forth, and P of C. And this is the naive assumption. That the features are independent given the class. And this can be more succinctly written as argmax P of C and the product of P of Fi given C. And at this point we can estimate these probabilities. P of C, probability of an email being spam, that's just the number of emails classified as C in our training set over all the emails in the training set. So if 50% of our emails in the training set are classified as C, then our P of C would be 50%. And the probability of Fi given C can be estimated as the number of times you see the word Fi over all the words in emails classified as C. For example, 33% of the emails in our training set are spam emails, and the probability of the word the given spam could be 1.56%. So 1.56% of all the words in spam emails are the. And once you estimate these probabilities this way, then we can compute this value with respect to spam and not spam and determine which one's bigger. And the bigger one is our class.